Okay, so I think we can start once again. Welcome to everyone and welcome to this new webinar. This one is the second webinar about the Python API in STKO, and here we have more attendees. And it will be focused on how to use the Python API to run parametric analysis in OpenSees and OpenSees MP. Okay, so I think we can start. I just have to share my screen. And here we are. Okay, so first of all, today we just released version 2.0.2, and there are some minor new features that are needed for this webinar. So you can go on the website and update it. So today's version, the current version is 2.0.2. As usual, you can reach the Python API reference manual here. Okay, so all the things that I will explain today, you can go and check it on the Python API reference manual. By tomorrow, you will have the video recording on our website, as well as all the input files that we are going to use today, okay? So the content of the folder you will see tomorrow is this one. You have 3 folders. The first one is the sequential TCL OpenSees, okay, which will be the starting project, okay, so the one that you will always do with STKO, so without parametric analysis. And then I will show you 2 different ways for converting this one into a parametric analysis, either by using OpenSees MP and just some TCO scripting, so without the Python API, or how to do parametric analysis with the sequential OpenSees, so running multiple sequential OpenSees instances directly from STKO using the Python API to parameterize your model and to run multiple analyses, okay? Perfect, so let me start with the first one, okay? So the first one has nothing to do with parametric analysis, it's just to show you what is the model I will work on and then how to convert it to a parametric analysis, okay? It will be very easy, so just a column. So let me go here and start with the sequential TCL OpenSees. Perfect, so this one is a very simple column, so just one element, fiber cross-section, reinforced concrete column. Okay, so I'm just going to show you just the pieces of the model. And this one will be used for the other 2 examples, okay? So parametric analysis using TCO and OpenSees MP, and parametric analysis using Python. Okay, so when you go into the model, you can see there are 2 selection sets. One for the top node, okay, to monitor the displacement on top, and one for the bottom node to monitor the reaction forces at the bottom. Then the geometry is very simple, it's just a single line. Then we don't have any interaction, of course, we have just one geometry. Then we have some definition, okay, as usual, the time series. So one linear time series for the gravity analysis. And then we have some path time series for the ground motions, okay, so for the transient analysis. Then the physical properties, we have a simple concrete O2, okay, and I'm going to go to Pinto model for steel rebars. Then the section. The section is a rectangular fiber cross-section. As you can see in the new version, we also have the quadrilateral meshing for fibers. Okay, so a simple fiber cross-section for a column, equally spaced rebars. Then this section is used into the beam section property using a simple standard integration rule, Lobato scheme, 5 integration points. Then the element will be a force-based beam column, linear kinematics. So we are not focusing on large displacement here. Then the boundary conditions. Of course, we have a fix at the bottom. Okay, so all degrees of freedom are fixed. Then we have a mass on top. Okay, to simulate the weight of the column and some weight coming from the above floor. And then we have a nodal force for the vertical action, okay? So this nodal force, keep in mind here I'm modeling in Newton millimeters, okay? So this one are 200 kilonewton here of vertical compression. So that's all for the boundary conditions, and then we have the usual time steps, okay? So the first one is the MPCO recorder. The output file name will be column. And here I don't really care about what I'm recording because actually I will show you how to parameterize these things, okay? So here I'm just recording displacement and reaction forces. Then we have the boundary conditions. And we just have a fix at the bottom, so nothing special. Then we have vertical loads, okay? So the single vertical load that we have here associated with the linear time series, right? Then after this we define the damping. Damping can be defined here or later on before the dynamic analysis, it's not important. Then we have a gravity analysis first, just 10 steps of gravity analysis, static gravity analysis, and then we apply the ground motion. We apply the ground motion using the uniform excitation. Okay, as you know, uniform excitation, you just have to specify the direction. Now we want to apply the excitation along the x direction, and the tag of the time series to be used for the ground motion. Okay, and this one will be number 2 here. Well, it's not important here. I have 2 time series. But as you know, even if I have 2 time series and I want to run a dynamic analysis for each one of them, using the standard approach, you can only run an analysis for one of them. Then you have to go manually here, okay, change the ground motion and run the analysis again. That will be the standard procedure. And I will show you how to parameterize these things in such a way that you will run one analysis for each time series. Then when we have defined everything for the dynamic analysis, just before the dynamic analysis, we define a monitor, okay? In the new version, and this one is very important because if you don't have the new version, you won't be able to run this, this example, because since the previous version, until the previous version, the monitor uses a built-in name, okay? The name was STKO monitor underscore the ID of the time step. So in this case, would have been STKO monitor underscore 10. What's the problem? The problem is that when we will use OpenSees MP, so multiple processors running the same script, they all will write, they all will produce the same monitor file, okay? So they will try to write on the same monitor file. And this one is not fine because actually we want one monitor for each process because each process handles one parameter, okay? So in the new version, we added an optional variable to specify a custom name, okay? So if you don't have it, it will use the, for backward compatibility, it will use the standard default naming. Otherwise, you can check this one and specify your own name, okay? So in this way, you can make sure that each monitor has a proper name. Okay, and you will see this topic later on. Okay, and in this monitor, I'm just monitoring the displacement from the top selection set against the reaction force on the bottom selection set. Okay, then I'm scaling this one so that I have meters, and I'm scaling the reaction force so that I have kilonewtons. Okay, and finally, the dynamic analysis, just a very simple setup for a transient analysis. Okay. So this one is the standard way you would do a dynamic analysis in OpenSees, either with this simple model or more complex models. The steps are them, okay? But in this way, you can run an analysis only for one time series. Okay, so let's try to run this analysis with OpenSees MP, and let's see what is the output. Okay, so you have just one command line because you have only one OpenSees. As you can see, also the monitor has been improved a little bit because for parametric analysis, it would be nice to have multiple plots at the same time. So before, you had a combo box here, actually it was in the middle on top, where you could choose what is the monitor you want to see, okay? Now in this case, I have only one monitor, so there's no problem. But imagine if you have many monitors, okay? One for each parameter. It's very annoying to look at them one by one. You may want to look at them all at the same plot, so you can superimpose them, okay? And you will see this one will be very nice for parametric analysis. And also down here you have the random seed, because now the colors are random, so you can change it. You can change the random color here. Okay, so this one is the output you have with the first time series. Now let's see how we can parameterize this model. Okay, so as you can see here with the sequential TKO OpenSees, I have the standard output. So I have only one MPCO file for the output and only one monitor output. So pretty standard. Now let's say I want to make it parametrics, okay, so that I can just run it once and it will run one analysis for each time series. Now to do this, you can open this one, parametric TCL OpenSees MP. Okay, so here I'm not using the Python API. I will talk about the Python API in the third example. Okay, because when you want to run parametric analysis, you have two choices. You can either use OpenSees MP, doing some TKO scripting, or you can use the Python API inside STKO to directly parameterize the model here. Now this one is a little bit more complicated, but indeed it will be more powerful. So I will start instead with how to parameterize a model using TCL. Okay, so basically this one is the same model you have seen before with the 2 time series. Okay, now as you can see, none of them has been used because I will change this model in such a way that each processor takes the right time series. Now before explaining what are these new custom commands that I added, probably we need to do some introduction to OpenSees MP, some very basic introduction. So just to show you how OpenSees MP works. Okay, so let me create a new folder and let me name it test MP. And here I want to create a new text file. So let me call it test.tcl. And I will open up with a text editor. Okay. Now at the same time, I want to open a command shell here. So because I want to run OpenSees manually now in this little test. Okay. So how you open a command prompt here? So open PowerShell, and let me put it here. Okay. So let's go back to the script. Now let's try to write something. Okay. So let me say set PID. Let me increase the character a little bit so you can see it better. Get PID. Now this one is an OpenSees function that returns the ID of the current process. Okay, and so this one will be set into this variable. And then I will try to print something on screen like hello from processor PID. Now let's see what happens if I run this script. So let me first open OpenSees sequential. Okay. Now I have OpenSees installed here inside C, OpenSees solvers, OpenSees. Now I will first run it with standard OpenSees, and then I will run it with OpenSees MP to see what are the differences. Okay. So this is the way you run OpenSees manually. So you call the batch file that executes OpenSees, and then you give it the TKO file as a parameter. Okay, so I run this one, and I simply say hello from processor 0. This happens because in OpenSees MP you just have one processor, and the processor numbering starts from 0. Okay. Now let's try to do the same with OpenSees MP. Okay. So C OpenSees solvers, OpenSees MP. Now for OpenSees MP it's pretty much the same thing. So you have the command before, then the TCL file, in this case it is test, and then the number of processor. Now I want to put, let's say, 4 processors. Now what happens is that I will see 4 times the same string. Okay, hello from processor 0, hello from processor 1, processor 2, and 3. Okay, And then after each string is written, I see process terminating 0, process terminating 1, and so on. So what it is saying is that even if you run only one OpenSees MP, actually this OpenSees MP is being called through the MPI executable that runs the same script on all the processors you specified. So here I specified 4 processors. The same script will be run on each processor, and each one will produce a different output. In this case, because my variable is parameterized according to this function, and this function returns a different number on each processor. Fine. Now this one is fine. This one just gives you the first important note. So OpenSees MP runs the same script on each and every processor. So this one is fine, and you can understand that you can use the ID of the processor to do some parametrization. Okay. So this one is pretty easy, but you have to take care of this thing, because let's say that here you want to write something on a file. Okay. Now with standard OpenSees, you would say that set f equal to open output.txt in write mode. Okay. Then you want to write something. So puts hello from processor PID, and then you close the file. Now what's going to happen here? Since I said that every single line in this script will be processed by each and every processor, all of them will try to open the same file and try to write on the same file. Now let's see what happens if all processors are trying to do the same thing here. Okay, nothing bad happened. Oh, I have a puts here that is wrong. I did puts on F. Okay, so I want to put this string inside the file. Once again, perfect. Now if I go in this folder, first of all I see just one output, and this is perfectly normal because all the processors are trying to open the same file. Now let's see what I have inside. I have only one row, and this row is from processor 3. It's completely random. Probably it can be processor 1 or processor 2, the first one that arrives. Okay, so in this case it's processor 1. Then I do it again, and it is processor 2. It is completely random. So one thing that you understand here is that every time you need to use output files, you need to make sure that every processor writes onto a different output file. Okay, so when you have to read from a file, it's perfectly normal to read from the same file, but when you have to write something, you have to parameterize also the output file. Okay, and this is important because I will show you now how you can parameterize the output database and the monitor file. Okay, now there are many other things that you need to understand about OpenSees MP, but these are the two most important topics for this webinar. So you have to understand that every single line is processed by each and every processor. You can parameterize, so you can understand what is the current processor just by using this function. And you have to pay attention to files whenever you want to write on them. Okay. So let's close this one. I don't need it anymore. And now we will proceed with the sequential OpenSees. Okay, so this one is the same file you have seen before, same definitions, properties, element properties, conditions. Now, what did I change? Now, just before the recorder, I defined a custom command which is called declare parameter. Okay, so this one is a kind of a pre-processing step where I read the current processor ID and I do some parameterization according to it. Okay, so the first one will be a custom TCL script. Here I have a note. Watch out that in OpenSees MP the processor ID is in the range 0 to n, so n excluded, so 0 to n minus 1. So the first thing that I do is to create a variable called param ID, which should be equal to the current processor ID. Okay, so set param ID equal to get PID. Let me make it a little bit larger. Okay, so this is the first thing that you need to do with OpenSees MP when you want to parameterize something according to the processor. Then in this model, what I want to parameterize is the time series or the time series tag to be assigned to the ground motion. So what I really need to parameterize is the ground motion ID. Okay. Now in my file, the first one has the ID equal to 2, and the second one has an ID equal to 3, because the first one is used for gravity analysis. Now, since param ID starts from 0, I can easily get the time series ID just by adding 2 to the current processor ID. Okay? So in this way, the first processor will evaluate this one as 2, so it will point to the first time series. The second processor will evaluate this one as 3, so pointing to the second time series. So this one is pretty easy. I parameterize the ID of the time series. Now I need to parameterize something else. I need to parameterize the name of the MPCO file. Okay? So if you remember, in the previous example, I directly wrote a name in the recorder called column. Okay? Now in this case, I want to make sure that every processor writes to a different file. So I create another variable called MPCO fname, which stands for file name. And this one should be equal to column underscore param underscore and then $sign param ID. This one in TCOL will be evaluated with the variable applied here. So it will be column param 0 on processor 0 and column param 1 on processor 1. That's fine. Now you need to do something else. Because when I define this variable here, then I can use it in the name of the MPCO recorder. So instead of writing a full name here, I just write the $sign MPCO fname. So when this one will be written in TCOL, for example, let me show you if I write this one, and I go here, OpenSees TCL MP, I go into the analysis time steps, and I see that the first, let me go to the MPCO file name, recorder MPCO, okay? Now I have $sign MPCO fname, but MPCO fname is a variable that I set before. So this one will actually be evaluated by TCOL using this name here. So my output file will be named column param 0 or column param 2 according to the current processor. Now there is a small problem. When you write the name of the recorder inside STKO, STKO doesn't know that this one will be a keyword in TCOL, okay? So he thinks that this one is the real name that the user wants to give to the output. So you will see here that you have an MPCO CData, which is something created by STKO before OpenSees creates the actual MPCO file. And this one will have a wrong name, okay? Because then TCOL will change this name. So that's why I have a small script here, which is this one. Pretty simple. You can just copy paste it every time you want to do this. And this one is simply used to copy this fake name here into the real name that TCOL will evaluate, okay? Now, just to show you how it works. So it takes a name where there is the real $sign character. Okay, that's why I'm using the escape character here. And this one will be the name created by STKO. So this file. And then I will change this one with the new name, which is the same but without the escape $sign, with the escape character, which is this \. In this way, TCOL here will not evaluate the $sign as a command in TCOL, but here it will, okay? So it will change every file with this name to a new file with this name here using the copy function, okay? So just to show you what this code will do, is simply, I put an error here so it will stop and it will not go on with the analysis. But now you will see that if I run this one, he will copy this into a name called column param 0, okay? So I run this one, then I have an error here because I put the error on purpose. And then you can see that this one has been copied into column param 0. Now you have only column param 0, not column param 1, because I just ran with one processor. But later on you will see that it will create one of these files, each one for each processor. Okay, so this one is the main aim for this piece of code. And this one is all documented, okay, the explanation for this one. So let me remove the error code and we are fine. So with this first small TKO script, we just declared all the parameters that we need, okay? So the time series ID and a parametric name for the recorder. That's why here I put a note here, recorder parameterized, okay? Because now the name depends on the current processor. Now the constraints, the vertical load, damping, gravity analysis are all the same. Another change that I made is the ground motion, because the ground motion now should be parameterized as well, okay? So I cannot use the ground motion command, the uniform excitation command in STKO, because in STKO I have to statically give it a time series. Instead, I want to convert it into a custom command, which is very easy for the uniform excitation. You just have to write the pattern, uniform excitation, the ID of the uniform excitation, the direction, that will be 1 along the X, and then the tag of the time series for the acceleration. That's why here I use the Gmotion ID, which is exactly the time series tag that I created here, okay? So in this way, the Gmotion ID in this piece of code, it has 2 for processor 0, so it will take basically this time series, and has 3 in processor 1, and it will take the last time series, okay? So actually here we are fine. The only last thing that we need to parameterize is the name of the monitor. As I said, because if you leave it with the same name on all the processor, it will monitor only one of them. Okay, so the first one that tries to open that file. Instead, we want to monitor all of them so that we can see all the monitors in the same, all the monitor graphs in the same monitor widget. Okay, so what I do is simply to take the same name that I gave before, and then I append this function that in TKO will be evaluated with the ID of the processor, okay? So pretty easy, there is nothing to do here, just you put this one, and TKO will evaluate this one as 0, 1, 2, 3, 4, and so on, okay? So once you have done this, you can run the analysis, but you cannot run the analysis from here, because here if you put OpenSees MP, you cannot set up the number of processors, because OpenSees MP in STKO is meant to be used for parallel analysis of large models, okay? So you have to take one large model, partition it, but that is not a parametric analysis, okay? But this is, you don't have to worry about this, because you can simply write the input file, okay, like this. You write the input file, you are here. Once your input file are written, you can simply open a command shell, okay? So if you don't know how to do it, you can just click on Shift and right click, or you can go in File here and open a command shell, okay? So open a command shell in this folder, which is the folder where you produce your TKO file. Then you need to type the command for OpenSees MP. In my case, I have it here, OpenSees solvers, OpenSees MP. Then the TCL file name, which is main.tko, and the number of parameters, okay? Now we have just 2 time series, so I just need to put 2 here. So run OpenSees MP with the main TCL file on 2 processors. So if I run this one, now you will see that I have a monitor here, and I have 2 graphs. So if I switch to the multiple flag here, you can see actually all of the graphs at the same time, okay? You can switch on and off one of them, okay? It is not important, you can see all of them. You can change the color, okay? So here the analysis is done for both processors, and you can have a look at all the files, okay, here. So this one is pretty easy. It's a pretty easy way to run a parametric analysis with OpenSees MP directly from STKO, just by using some Tcode scripting, okay? Unfortunately, this approach is very easy and useful when you have to parameterize simple things like the ID of the ground motions, which is pretty useful for dynamic analysis when you have to run the same model for multiple ground motion. But if you want to parameterize other things like the geometry or the material properties, and you have your model done in STKO, it is not very convenient to do it with OpenSees MP. So that's why you can use another approach, which is using the Python API inside STKO to parameterize and change your model, and then run one analysis with the sequential OpenSees for each one of your of the changes that you made to your file, okay? So let me save this one. So I will show you how to parameterize the same model, but changing some of the boundary condition that I have here. So now you are done with this file, and I will start now with the last one, which is parametric Python API. So let's go back and open the file in parametric Python API. Once again, this one is the same file as before, so pretty similar to the other, at least in the geometry, selection sets. Now we have only one time series, a linear one, because here instead of doing a gravity plus dynamic analysis, I'm doing a gravity plus a pushover analysis, because now I want to parameterize the vertical load to see the effect of an increasing vertical load onto the capacity of this column, okay? Now this is pretty standard, but it is useful to understand how a certain parameter affects the response of your model. Okay, so when you open the parametric Python API, in the input folder, you will see only two files, okay? So the SCD file, which is the input file for STKO, the one that I opened now. And then you have a small script called parametric vertical load that we will be using in this webinar, okay? Now, if you have never used the scripting editor before, I will show you how to add this folder to the script explorer. So the first thing that you have to do is to add the folder of this example into the script explorer, like this. So you go here on the webinars, you go in parametric Python API, and you click select folder. Okay, so that now you can access this one. Let me close it. When you have this file, you double click it and you can edit it, or you can have a look at the file here, and you can run it, of course. Now, what I want to do is to, let me go in conditions. The rest of the model is the same as you have seen before. So we have a recorder, we have the constraint, then we add the vertical load here associated with the linear time series. Then we run a gravity analysis. We keep the load constant. I create a monitor. Then I apply an horizontal load. And then I do a pushover, okay? So pretty simple. The vertical force now has a random number. It is not important that it is this one, because now we will change it through the Python scripting, okay? Then the pushover, the push curve, the push load is just a reference load. It can be 1 or any other number, okay? And this one are the two boundary conditions that I have in terms of loading. Perfect. So now the recorder is not parameterized, as you can see. Just the starting name column. I will parameterize it later on. Actually, it is not necessary to parameterize it. Then you add the boundary condition, you add the load, you add the vertical load. Okay, so there is nothing special here. Also, the monitor is not parameterized here. I will change it. So I will parameterize it through the Python code. Let me show you. So when you want to parameterize some model using the Python API, the first thing that you have to do is to import the PyMPC module, okay? So in this case, I imported everything from the PyMPC module. Then I imported these two functions, runSolver and writeTCL, which are basically the same two functions that are called by STKO when we run the analysis. so run solver, or the right equal is the function that we call when we click here, write input file, okay? Actually, when we click on run, STKO calls first this function and then this function, okay? Instead, when you write the critical file, it only calls this function. Then we have a few other modules that we need. So the OS for standard operation, the shootil for copying and deleting files and folders, the subprocess, which is a module used to run another process, and the time. I just use this module to sleep a little bit and wait before running all the OpenSees terminals. So the first thing that I do is to clear my terminal so that here I have a clean output before running my script. Then I get a reference to the KAI document. KAI document is the preprocessor document, okay? So KAI stands for Computer Aided Engineering, pretty much like CAD, for example. So I get the preprocessor document. Then here I need to get the current command name that the user chose, for example, OpenSees, and there is a function in app called hasCurrentSolver to make sure that a user has OpenSees in his computer, okay? Because if you don't have OpenSees, it will show an error, okay? I cannot find that solver, please check your kit manager. If you don't have this error, it will go on, and it will try to get the current solver command, okay, by calling this function, current solver command, and it will give me OpenSees, or actually it will give me this function here, this first part of the string, okay, so that I can get it and run it later on. So for example, if I raise an exception here just to stop the execution, you will see that if I have OpenSees here, this one will print C, OpenSees solvers, OpenSees, okay, here it is. But if I change it to OpenSees SP, for example, I run it again, and it will print OpenSees SP, okay? So now let me remove this exception. So this first part of the code is just to get the command for the current solver, because then we will use it to run OpenSees. Now I need to define the parameters. Now in my case, I want to parameterize the vertical load, okay, starting from 0 down to minus 400 kilonewtons, okay? So 0, minus 100, 200, 300, and 400. Okay, so 5 parameters, so I need 5 processors. Then I need to parameterize something. I need to parameterize the boundary condition, which is this one. So I can get the condition by calling document.getCondition and then the ID of the condition, which in this case it is 3. Okay, so let me make some room here. Okay, so I get condition number 3. Then I need also to parameterize the monitor. Once again, I need to parameterize the monitor name so that they do not overlap. Actually, there is not a problem for overlapping because all of them will be written in a different folder. I will show you. That's why, for example, we do not parameterize now the name of the MPCO recorder, but I want to keep this name parameterized according to the current vertical load so that it will be easy to identify them into the monitor when I will plot all of them into the same monitor. So I get a reference also to the monitor time step. Now, since the monitor it is a time step, I use a pretty similar function to this one, but instead of getting condition, I call get analysis step. Once again, here I need the ID. The monitor is the number 10, so get analysis step 10. Perfect. Now I need a list of working directories. Why? Because for each parameter, I will produce the TCL file into a subdirectory here. So we'll create 5 subdirectories, each one for a different parameter. Okay. Now, first I will perform a loop here to create these folders and to write the TCL file. And then after that, I will start the monitor. And finally, I will run the analysis. Okay. That's why I'm storing the name of the working directories here outside of this first loop. Okay. So this one starts as an empty list in Python. Then I need to do some tricks with the monitor. As you know, when you write the TCL file inside a folder, it will create a STKO monitor directory and a launch STKO monitor batch file inside that folder. But as I said, I will create 5 subfolders, so I will have 5 monitors and 5 launchers, each one of them inside the respective folder. Now the problem is that if I leave it as it is, every processor will run its own monitor. Instead, I don't want 5 monitors, I want just 1 monitor, okay? So I will show you what I do with these 2 variables later on. So here I do a loop over the parameters. So for PID in range length parameters, so PID goes from 0 to 4 basically, because I have 5 parameters. I get the current parameter. I update the conditions, so I check on get condition x object. So from the condition you can access the X object. X object is the external object that interfaces with OpenSees. From the X object I can get the attribute. The attribute is, for example, each one of these. Okay. Now I need to update only this attribute here, so I get the attribute by name F. Now this attribute is a 3-dimensional vector. So I get the attribute, I access the underlying data, which is a quantity vector 3. And here I set the value at the 3rd position, 2, because it is 0, 1, 3. Okay, 0, 1, 2 is 0 based. So set value at 2, and I set this value here. Then I do some stuff to notify the document that this condition has changed. Okay. Now just to show you, for example, here I start with minus 400, okay? And if I raise an exception here, raise exception, stop. Here you will see that I will stop at the first cycle in the loop. So the first parameter will be 0, okay? So let's try to run this one. Okay, stop. I go here, and the force vector is 0. And as you can see also here, I don't have any vertical force now. If I stop it only at the 2nd cycle, for example, if PID is equal to 1, it will first set it to 0, then it will do some stuff here, it will stop it to 1, and then this one will be 100, okay? So this is just to show you that this piece of code here is going to change the boundary condition. Then I do something similar to the monitor, okay? So first I make sure that the user is using the this one, use custom name. Use custom name here as a checkbox, because this kind of attribute is a Boolean value. So true or false. And then I set up the name. This name starts from force x, displacement x minus 400, but then I will change it. And I will change it using the same naming, but replacing here the real current vertical load, okay? So first I make sure that I use a custom name, and then I parameterize the custom name. Once again, I click on, I write commit x object changes to notify the document that something has changed. Once I finished my changes, I set the document as dirty. This one is actually used to let the user understand that something has changed into the monitor. So setting the dirty variable to true will allow the user to save the file, okay? Then I commit all the changes done up to then, and I run a regenerate command. This is not necessary, but it is fine, and it is nice to see it, because if you change something like, for example, the condition, you will see the drawing that gets updated. So you are notified visually that something is happening. Okay, so up to here, I finished changing my document for the current parameter. Now I need to create the current working directory, okay? So I want to write, I think we have something on the chat. Okay. Let me go here, doc area, YouTube, perfect. So I need to create the working directory. So output directory, now it will be equal to analysis, parametric vertical load. And here I will put the vertical load divided by 100 because I want it to be written in kilonewton. Okay, so this one is the name of the current subdirectory. It should be relative to the current working directory. That's why I didn't put anything here. Okay, so if this directory does not exist already, I will create it. That's why I need the OS module. So OS path is a submodule that allows you to understand or to find something useful for paths. Okay, so first here I check if this folder already exists. If it does not already exist, I create it. And I append this name to the list of the working directories I created before. Okay, so at the end of this loop, this one will be a vector of 5 components, each one containing the name of the subfolder. Fine. Now, when I created the output folder, I can write the TCL files for that parameter inside that folder. That's why I called it out dir, so output directory. So you can simply call the write TCL function, passing the current output directory inside this function. So this one will write the TCL files for this parameter inside this folder here. Now, all this piece of code here is just used to do something on the monitors. I will show you what. Now, before doing this, I want to not to let this piece of code run. Okay, I will talk about it in a while. Now, I just want to focus on the first loop, and let's assume I only write a TCL file without doing this. So if false, and I don't want to let this code run. Perfect. So we'll do all the loops just by going here. Okay. If I try to run this one, as you can see, the arrows are changing. Look at it. Okay. So 0, 100, and so on. If I go here, you will see that you have 5 folders from 0, 100, 200, 300, 400. Okay. Let me see, we have a question on a YouTube channel. Can you change the model using Python while OpenSees is running, or get, read, write results from the analysis when the program is running? Actually, yes. It's not so easy, actually, because you need to understand how the the subprocess popen function works. It can be done, but you need some experience with the communication between the processors. I will cover this topic in a future Python API webinar. In the meantime, if you want to understand how to interact with OpenSees from Python, you can have a look at the material tester. And in the material tester, we do exactly the same thing. Let me show you. In the material tester, you can go actually in C, program files, STKO, then you can go into external solvers, OpenSees, physical properties, utils, tester. And here you have all the files that we use for material testing. For example, you can open the tester 1D, and at a certain point, you will see subprocess. There is a popen somewhere, or not actually here, but yes, it is here. Prepare test. Then if you look at this file and run, okay? So in this file, I'm running the OpenSees using an asynchronous function, and I will listen to this function, okay, emitting a signal every time OpenSees gives me an output, okay? So it can be done, it's not so easy, okay? I will cover this topic later on. In the meantime, if you have some experience with Python and with inter-process communication, you can have a look at these files, and actually all the files that are here, to understand how we do it, because actually in STKO we do exactly the same thing, okay? So when I open this one, I click on test. I'm communicating with OpenSees, and while OpenSees is running, I'm getting the results, okay? So it can be done. Now moving back to our previous example, I told you that when you run this one, okay, so you're updating your model and you are writing the TCL file, but you're not doing anything else. So if you go into this folder, you will see that I have 5 folders, each one for a different vertical value, okay? And inside each one of them, I have the standard TCL file produced by STKO, plus a monitor directory and a launcher. And I have one of them for each analysis. Now this is a problem because if I have the monitor directory and the launcher inside each folder, when I will run OpenSees in each and every folder, I will see one monitor for each one of them. And I don't want to see 5 monitors. I want to see just one monitor that monitors all the analysis, okay? So this little piece of code is just used to delete the monitor and the launcher into the subdirectory. But before doing that, only in the first cycle, I want to copy it in the above directory. So I want to copy it here, okay? So now let me execute also this part of the script. Now, if I run this again, you will see that here inside the subfolders, I don't have the STKO monitor and the launcher, but instead I will have one monitor, one STKO monitor and one launcher here. Okay, so let's try to run this one. Go back here, and now you can see a launcher, a monitor folder, and in the subfolders you don't have any launcher. Okay, so this is fine. And finally, there is this last piece of code. Now the first one is used to run the monitor, and as I told you, when you want to run an external process, you can just use the subprocess monitor popen function. This one is a very simple implementation. Otherwise, you can also interact with it, as I did with the tester in STKO. But in that case, you need some experience. And in this case, we just need to launch the batch file and keep it open. Okay, so I don't need to wait for it. This one means launch it, but don't wait for it to be closed. Okay, so it launches the Python monitor and then goes on. Now, since this function will be very fast, but the monitor will take about 1 second to start, I want to wait. Okay, I want to wait just 1 second. After 1 second, I will run OpenSees in such a way that the monitor will be open pretty much at the same time OpenSees starts. Okay, otherwise OpenSees will start before the monitor, and since the analysis will be very fast, I won't see the beginning of the analysis. Okay, but this is not important. Okay, so this is the key of the topic here. Then once I open the monitor, I just need to go inside each folder. So for PID in range length parameter, I get the current working directory, and then I call run solver in this working directory using the solver command, passing the main TCL to the solver command. Here I need to pass an empty string because this one will be the number of processors, but since I'm running one OpenSees for every solver manually, I just need one processor for each one of them. Okay, so I'm running multiple instances of OpenSees. Then this last one is a flag. Okay, it can be either false or true. If you by default keep it to true, okay, because if you keep it to true, the command file, the command window in every folder will be left open. Okay, and this is nice because you can see if something goes wrong, you can see the error message there. Now, if I run all these things, I should see once again all these folders, then the monitor, and a series of OpenSees command lines. Okay. Now let me run this one. Now the monitor, the 5 OpenSees, and here I can go into multiple. Okay. And here I see all the force displacement curves. As you can expect, here I'm increasing the vertical load, I increase the strength, but I reduce the ductility. Okay, so pretty standard. This one is another way of running parametric analysis inside STKO using the Python API, changing directly the STKO command. So not working on TCL, just changing the STKO file, and STKO will produce a TCL file for this new model, this new updated model. Now, this one is the very first webinar on how to parameterize a model in STKO. So I did something very basic. So how you change a value inside a condition, in this case, the vertical force, or how to change a string, for example, the name of the monitor. But keep in mind that you can do much more complicated things. So in the next webinars, probably in the next one, I will show you how to do soil pile interaction and changing the parameters of the soil model and of the pile model, so even changing the geometry, okay? So it will be a little bit more complicated. That's why I started with the basic concepts. So if you learn these concepts and you go through the Python API reference manual, before the next month, you will be sufficiently prepared for the next webinar, okay? And in the next webinar, I will show you also how to change the geometry, actually how to create the entire model by Python, okay? Not just creating a model and changing some parameters, the entire model. So from selection set down to the last analysis step can be directly written in Python so that you can take advantage of just parameterizing few things, and then STKO will do the meshing and produce the TCOL file for you, okay? So try to understand the basic concept of this webinar, and it will be very useful for the next one. Okay, so I'm done with this webinar, and we have some time for the questions, if you have any questions. Oh, and of course, when you run OpenSees in this way, you have a lot of command windows, and you can close them all at once. Okay, perfect. Let me go back on out of full screen, and let's see if you have any questions. Is everything clear? Do you need some explanation of some steps that I did, something that is not sufficiently clear? Or some suggestions, if you have some suggestions how you would like to use the Python API, how you would improve it. So it looks like it was pretty clear. We have a question here. Okay, how useful is this parameterization process for a large model where we have, say, 1 million doves, 100,000 doves? Actually, this is a problem. I mean, when you have a very large model, you already need all the processor for that model. So probably it's not so useful to run parametric analysis, but actually it can be, at the same time, it can be useful because actually you can run one analysis and wait for the other, because in this case, I knew that the model was small. So I simply performed a loop and I simply ran an OpenSees instance without waiting for it to finish, okay? So I ran all of these instances at the same time. But now imagine that you want to do the same, so parametric analysis of a very large model. So each one of these calls will already take all the parameters, all the processors, because the model is large, and you want to use OpenSees MP using a partition model. So actually what you can do is to learn a little bit about the subprocess popen method. And this one, if you go on the Python documentation for this function, you will understand how to wait for this process to finish. So actually it will not be a parametric analysis in the sense that you wait for each, you run all the parameters at the same time, you run it one at a time, but the nice thing is that you can do a click and wait for all the analysis to finish, okay? So every large model will be run one by one. When the first finishes, the second one will be launched. But the nice thing is that you don't have to go inside STKO every time and change some parameter, okay? So you can do it all at once and wait for OpenSees to finish. So it still has some some usage cases. Can you use any distribution of Python? Yes and no. I mean, you can. We have a basic distribution of Python inside STKO with all the some of the packages that we need to use. For example, we can use NumPy, Matplotlib, and a few others. If you want, you can use your own Python distribution. If you want to use your Python distribution because you made some change to your Python or you have other libraries, you can do it. Try to use the same Python library that we are using. Otherwise, you may have some problems. In any case, probably it's better if you think that you need some other modules that we did not include inside STKO, you can simply write on our forum a suggestion to include another library, and we will include it in our Python version, so it will be easier for you. Okay. I assume that you can also connect to Python libraries like SciPy and other, for example, for optimization. Of course you can. Of course you can. This is the main reason why we started creating the Python APIs, because you can run parametric analysis or optimization analysis, so where you can start getting the output, doing some calculation, and change the model according to the calculation of the output. This kind of operation will be a little bit more complicated, so I will start. I will explain how to do them, but later on in this webinar series, because first thing is that you need to understand how to parameterize a model, how to use the Python API, and once we have all this concept pretty clear, we can start putting them all together to understand how to interact also with other libraries, okay? But yes, you can. Yeah. In fact, with Python, you can do many things. Versions of Python is used to 3.6.2. Actually, if you want to see the Python, you can also put here sys.version, and you will see the version of Python that we are using here. But it is 3.6.2 or 4, I don't remember. Let me see. Let me print. It should be import sys print sys version, if I remember correctly, and writes an exception. (3.6.6). Okay, here 3.6.6, and then you have the build and the stuff here. So if you want to make sure the version that I'm using is this one. If you want to know what are all the libraries that we are using here, so probably you may, if you are fine with the libraries that we are using, you don't need to use your own Python distribution. Otherwise, if you have other libraries, you can use your own. You can put them inside STKO, or you can just give us a suggestion to build other files, so that in future versions we will include those libraries as well. You can go here into program files, STKO, Python packages, and these are the ones that we included, okay? Yes, basically now all the other webinars that I will do will be focused on Python, on how to customize your model, how to do all this customization. While my colleague Francesca instead will start a new webinar series for learning the basics of OpenSees with STKO. So now, from now on, we will have 2 webinars each month, okay? One with the Python API and more advanced stuff, and one starting from 0 to learning completely OpenSees. Okay, because probably someone is interested in Python, but many other users are still interested in learning basics of STKO and OpenSees. Okay, So from now on, you will have two webinars each month. Do you have any, for example, any suggestions on the future webinar that you would like to see about the Python API? Some kind of work that you would like to see? For example, the next one will be soil pile interaction. So it will be a soil model with an embedded beam element for the pile and contact elements. And I will show you how to create the entire geometry. So the solid model, doing the Boolean operation, creating the beam, assigning the beam section, everything in Python so that you can parameterize every single aspect of the geometry, okay? But if there are other ideas that you have or other suggestions, please you can give us suggestions, okay, so that we can schedule the next webinars. Oh, and we actually opened a specific portion of the forum for the Python for pre-processing and post-processing. So if you have any questions or any doubt, you can write there, okay? And now, little by little, we will start using Python to extend the capabilities of STKO. Guido has some suggestions. Okay, later on. I imagine you have too many suggestions. Okay, so if there aren't any other questions, I would like to thank you everyone for taking part of this webinar. And don't forget to follow if you're interested in the basics of OpenSees and STKO, the next webinar series given by our colleague Francesca. And see you on the next webinar. Hi everyone. Hi Dennis.